Okay, so welcome back. The plan for today is to go through 4.2 and 4.3, wrapping up what we're going to cover in Chapter 4. Note that there are a couple extra sections in Chapter 4, but just the way that our college chooses to kind of split the material up between MAT090 and MAT108, we're not really going to talk explicitly about slope or like slope intercept form, some of those kind of things. That topic is we kind of leave till Math 108. So 4.2 and 4.3 will be our last sections in Chapter 4. And next week, so this coming week, however you want to say it, the Unit 1 exam will be available from 9 a.m. on Monday through 11:59 p.m. on Sunday. The material is chapters 1 through 4, of course, only the material that we are covering in Chapter 4. The sample exam I'll have posted probably later this morning, probably shortly after we end class this morning. I just have to double check and make sure that what we get through in class today, just make sure that there's nothing on the exam that if it takes us a little longer to get through 4.2 or we don't quite get through 4.3, something like that. So make sure that I don't have to adjust any material or anything like that. I don't think I will, but that will be posted later today. Just a reminder, no Proctor for the exams, just because of the technical issues we've had. Really wouldn't be fair to you all to, with the stress of an exam already, to kind of add that on top and wonder, wait, is the tech going to work right? Is it going to glitch out or something? So no Proctor for the exams. And probably the most important thing, don't wait until the last minute to take the exam. And the exam's open Monday through Sunday, so waiting till the last minute is like waiting till Saturday or Sunday. So I would strongly recommend that you plan on taking the exam on or before something like Thursday night. That way, if anything goes wrong, if there's a power outage, an internet issue, a tech issue, some problem with your computer that it doesn't want to connect to WebAssign or something, that gives you quite a bit of margin to get that worked out, to contact me, to contact tech support, or if needed, you could go to a local library to take the exam, or go to a CCAC campus to take the exam, like on, say, Friday or Saturday or something. If you wait until Sunday evening or something to take the exam, you just have far fewer options and far less time. So, and the parameters for the exam, it is closed book and notes. You can use a calculator that's only a calculator, so no phones or online tools, things like that. And these days, I think it is important to point out that no AI use either. So no asking ChatGPT or something, or so just to be clear about the expectations. And then the sample exam that'll be posted this morning or afternoon should give you, sorry, my allergies are just going bonkers with the temperature swings. The sample exam should give you a really good idea of the type of material that will be on the exam, the length of the exam, the depth and breadth of the material, as well as giving you a chance to kind of practice working in the testing environment. And it's still through WebAssign. It's still so the sample exam you'll see pop up on WebAssign just like any assignment, like it'll be in that same list. But when you click on it, it'll be an exam type of assignment instead of a homework type of an assignment. So it'll have a timer, that kind of thing, for the actual exam. The actual exam will have a timer. The sample exam won't. But yeah, so the sample exam will give you also the ability to just practice all of that. Practice entering your answers, making sure that everything kind of goes smoothly from the kind of administrative side of things as well. Yeah, if you have any questions about the exam, send me an email or pop in office hours. And when I post the sample exam, I'll send out an announcement as well, and just to let everybody know that it is posted, it's available. And if I have anything that I forgot to mention here, or just a recap of what I said here. Okay, and the quote of the day today is actually from one of my wife's previous colleagues. She often liked to say, velocity is a vector quantity. And if you're not in the the kind of nerd circle, sometimes you might say, what does that even mean? Well, if you've seen Despicable Me 2, I think the villain's name is Vector, and because he has both speed and direction, or magnitude and direction, or something like that. But that's, that is true about velocity. Um, so a lot of times we kind of colloquially use the term velocity and the term speed to mean kind of the same thing, just how fast you're going. But really, velocity is when speed, how fast you're going, is coupled with a direction. So if you're going 30 miles an hour, that's a speed. If you're going 30 miles an hour in the direction northeast, that's a velocity. Um, and she would say this because, from her perspective, a lot of times people really focused on speed, so to speak, metaphorically speaking. They really just wanted to jump in and get started on this project, or let's just get this initiative going, or something like that. But they focused on speed and didn't look at all at direction. So they just wanted to feel like they were getting something done, or they wanted to prod other colleagues into getting something done, and not taking the step back and saying, okay, like if we're just staring at our feet and making sure our feet are moving really fast, I don't know if we're going to reach our goal because we might be pointed in the wrong direction. So I think there's a trade-off to be had there, right? And there's a balance to be had there. And my kind of general thoughts on this are that effectiveness, so your essentially ability to reach a goal, is something like the product of efficiency and effort. If you put in a ton of effort, but you have zero efficiency, if you haven't done any planning, or haven't pointed yourself at all in the right direction, then you have like 0 times a big number. That's a very low effectiveness. On the other hand, and this is kind of my tendency, there are some people who really like jump in and just get it started. People, that's not my tendency. My tendency is on the other extreme, is to spend tons of time pointing myself in exactly the right direction before I get moving. But if I spend all my time pointing myself in the right direction, I actually never move forward. So, uh, right. So if you put in zero effort, but put uh, all of your time into efficiency, that doesn't make for a very productive day either. So I think there's a balance there. And in particular, if you realize that you're pretty far on one side or the other of if you tend to strongly prioritize one over the other, if you can recognize when you're doing that, and sometimes I just have to take a step back and say, okay, I've got it planned out enough. It's good enough. Let's just start on this. And then sometimes the folks who are the go-getter, just jump in and do it, folks need to take a 15-minute break and just say, okay, let's take 15 minutes, 30 minutes, draw out a plan of attack for this. And so something like studying for an exam, right? We have an exam coming up, could follow the same thing. If you just say, okay, I gotta start studying. I have 2 hours. I'm just gonna start hitting the books, and you just pick random topics or something and start going through them, or pick random homework assignments and start reworking them. Okay, that's putting in some effort. You're going to move forward, but is that the most efficient use of that time? Could you take a step back, spend 15 minutes, look briefly through the previous sections, and say, oh yeah, I remember this one. I'm pretty good on that one, but this one I really struggled with, and really focus your effort. So focus your study time on the sections that are the most high yield for you, or vice versa, right? If you're the kind of person who over plans, maybe you got to say, okay, I spent 15 minutes planning my study time. Now I got to switch and actually do the studying. Um, and then, one other thought on this is more kind of career oriented, but you can be very effective at something. You can be moving very clearly toward a goal. But then the question is, what is the relevance of that goal to whatever you're interested in optimizing? So if you're thinking of this in the context of like building a career and moving up in your career, and something like that, getting a promotion, if you go into your boss for your annual review and they say, what have you done this past year? And you say, I got really good at playing the piano. Um, for most of us, especially if you're, say, a nurse or an engineer or something, your boss is probably not going to be super impressed by that. They might say, okay, that's cool, but what have you done that's actually relevant to me, right? What have you done that's actually beneficial to the company? And that's what you might call impact is how effective are you at something versus how relevant it is to the company. So now we shouldn't only do things that are relevant to our jobs, of course, but if we're if we're taking a chunk of time out of the day and saying, I want to get better at something to further my career, if that's my goal, I might want to look at the things that my company values and say, okay, what are the things that they value? And can I pick one of those things out that I'm interested in, that they find relevant, and where I think that I could have a pretty good amount of effectiveness in that area and really boost my impact to the company. This idea of outsized impact was a buzzword from a couple years ago, but um, you know, buzzwords do tend to have some grounding in reality. All right, so that is the collection of thoughts for today, the quote and the information about the exam. So we are going to continue on with chapter 4. And we have an example and an exercise that's kind of just a refresher from last time. And then we'll move into, well, 2 exercises, and then we'll move into um, the job of combining the 2 ideas together, right? So taking our tabular representations of solutions and our graphical ability to plot points and combining those together some way. All right, so let's look at this first example here. Again, this should be a refresher from last time, so it shouldn't be anything super new. I'm looking to find 3 solutions for this equation, 2y minus 4x equals 15. I might notice it's basically in standard form, ax plus by equals c. So my variable terms all on one side and my constant term on the other side. And I might be looking for nice solutions here for integer solutions, x and y. So if I choose, say, maybe x equals 0, then I have that, well, 2y minus 4 times 0, 2y equals 15, or y equals 15 halves. Maybe I'm not super happy with that. Maybe I try a different one. What about y equals 0? Negative 4x equals 15. Going a little quicker than I did last time because this is kind of a recap. Or x equals negative 15 fourths. That also seems like kind of an annoying point to try to plot. I might actually look at my equation and realize that for integers x and y, each of these 2 terms on the left side are even, 2y and 4x, and their difference is even. So an even number like 0, 2, 4, 6, 8. And the right-hand side, 15, is odd. It's an odd number. I'm actually not going to be able to find nice integer solutions for this. It's just the way that this one works out. So maybe I'll try to get solutions where the denominator is not some crazy denominator. I don't want to end up with like, something over 8 or something like that, or even something over 4 might be a little more difficult to plot, but 0, 15 halves. 0, 7.5. Okay, I mean, I've got to accept halves in this case, but I can try to use uh, fractions with a small denominator. Let's try x equals 1. So I have 2y minus 4 times 1, 2y minus 4 equals 15. If I add 4 to both sides, I get 2y equals 19, y equals 19 halves. So I have 1 comma 19 halves. That's almost 10. That's like 9.5. Remember, my kind of general criteria were if I can get integer points, I like that. And I typically want the magnitude of both my x and y coordinates to be less than 10, because that just tends to be what my graph axes are labeled. That's not some kind of math rule or anything like that. It's just that tends to be the set of axes that we typically end up using, minus 10 to 10 on both axes, and staying between minus 10 and 10 for x and y just makes our lives easier. So we just barely made it there. If I go up in x, if I go up another one, and if I go up to x equals 2, I see I'm going to be adding 8 to the right-hand side. That's going to push me over the y equals 10 kind of soft boundary. So maybe I'll go down to x equals -1. Now I have 2y minus 4 times -1. I think that's a plus 4 equals 15. Subtract 4 from both sides to get 2y equals 11 and y equals 11 halves. So -1 comma 11 halves. And these will be three solutions for our equation, 2y minus 4x equals 15. Again, just as a reminder, -15 force comma 0 is also a solution. It's a perfectly good solution. It's just one that is kind of going to be a little more inconvenient for us to graph. It's just going to be practically a little more challenging to plot on, a grid line setup like this, or on, say, a WebAssign graphing tool, something like that. It's going to be a little harder to pinpoint that quarter of a unit than certainly an integer coordinate, but we don't have the fortune of having that ability in this case. So maybe I'll go with the halves. That's probably going to be a little easier for me to pinpoint when I'm making my graph. Okay, so let's go through these two exercises. I'll give you about maybe about 5 minutes for the two, just to kind of get it refreshed in our minds. So here you're not given any choices for X or Y to find the other one. So you need to kind of come up with your own choices for X or Y, find the corresponding X or Y to whichever one you pick. That gives you an ordered pair. Come up with 3 ordered pairs for each of these two exercises. And yeah, we'll touch base in a couple minutes, and I will work on this along with you in case you get stuck anywhere. Okay, it's just about 5 minutes, so let's touch base. So for the first one, y equals 5x minus 7. I tried x equals 0. That seemed like a pretty good one to start with. And I got y equals negative 7. That seems to work out pretty nicely. X equals 1 corresponds with y equals negative 2. Also pretty nicely. Works out pretty nicely. If I try, say, x equals negative 1, I find y equals negative 12. Again, perfectly valid solution to the equation, but just not very convenient for us to graph, as most of our graphs are stuck between negative 10 and 10, at least by default. So let's try for another one. If I pick x equals 2, I get y equals 3. Another good point, right? Um, so there's a little bit of strategy here, especially when you're working on WebAssign. If you get a point that's kind of wonky and difficult to plot, just get another point. Just pick a different one that's going to be easier to plot. I guess as an aside up here also, if I had done y equals 0, if I had looked at that one, um, here it was kind of obvious that I wanted to choose values for x because things were already solved for y in terms of x. But if I had decided to do y equals 0, I would have got x equals 7/5 and not an integer coordinate. I'd prefer something that's an integer coordinate. So these would be three ordered pairs that represent solutions to this equation, or which we'll think about in a minute here, which we could plot on a graph. Similarly for the second exercise, and by the way, these aren't like the best three or something like that, or the only three. You could have had a different selection of three of them. So long as we probably have a preference for sticking between negative 10 and 10 on both coordinates, and probably sticking to integers when that's feasible. So, but if you had, what would it be like? X equals 2, or sorry, x equals 3, y equals 8. That would be another good one. So if you had that one, that would be another good example. Okay, let's look at the next exercise, 3y plus x equals 8. Here, if I try x equals 0, I get 3y equals 8. Y is 8/3. That's not an integer point. Again, 0, 8/3, perfectly valid solution to the equation. It can, in theory, be plotted on the graph, just practically speaking, a little harder to plot. Let's try for an easier one. If I try y equals 0, well, 3 times 0 plus x, that's 8. Then we just get x equals 8. That's a good one. So be a little careful. We have y equals 0, x equals 8, but make sure it's 8 comma 0 when we write it over here. Don't get the x and y backwards. If we have y equals 1, 3 times 1 plus x equals 8. X has to be 5, so 5 comma 1 for a second point. If I tried maybe y equals negative 1, I get x equals 11. That's not between negative 10 and 10. Let's try for a different one. But y equals 2 seems to work. Gives me x equals 2, so 2 comma 2, our third coordinate here. And again, you could have had other coordinates. These aren't like the only three or the best three. If you found other coordinates with integer values for the coordinates, they're between negative 10 and 10. Those are perfectly valid and just as good as any of these. Okay, so now let's take a look at graphing. So that's really the whole crux of this chapter, and we really haven't graphed very much at all yet. We've plotted a few points here and there, but that's about it. So let's fill in the following table. I've already filled in the associated certain x values with the associated y values. And here's our graph, y equals 5x plus 1. So we have a point like 1 comma 6. We have a point like 0 comma 1. We also have this point 3 comma 16. Right? I'm not so sure about this one. We might want to redo that one. But let's just plot these other 2 points to start with. So this is my x-axis, the horizontal axis, and my y-axis, the vertical axis. By default, that's just what we call the x and the y-axes. And in our ordered pair, the horizontal component comes first, the vertical second. Why do we label them this way? Why do we make this decision? Well, it's just convention. We needed to decide a way to do it. And this is how we decided to do it. So x equals 0 means I start at the origin. I start here at the origin. How far do I go horizontally? I go 0 units horizontally. So 0, 1, go 0 units horizontally, and then go 1 unit vertically. So maybe I think I'm actually going to plot these in red just because it shows up a little better on the bluish background. So blue and green tend to blend in a little bit, and a lot of the axes and things are already black. So we'll do it in red, even though red looks a little jarring sometimes. So that's 1 point. Another point is 1, 6. Now I see if I went over to 3, 16, I'm like all the way up here somewhere. That's like off of my graph. I guess I could extend my graph and add some more tick marks going vertically, but that seems like a bit of a pain. I'd prefer not to use this point. Can I find a better point to use? What if I use, well, what about -1? X equals -1, y equals -5 plus 1 is -4. -1, -4, that seems like a nice point to use. I'd rather use that one. So I go to -1, I go left 1 unit on the horizontal axis, and then down 4 to here. Something I might notice about these 3 points is they lie on a straight line. In fact, we've been talking about things like this. We've been calling them linear equations the whole time. Why are we calling them linear equations? That seems like a strange way to describe this algebraic structure. Well, in fact, when we look at solutions, XY solutions to an equation like this one, like y equals 5x plus 1, or like any of the ones that we've really seen so far, we notice that these points fall on a straight line. I'm going to try to draw a reasonably straight line here. Okay, yeah, so good question in the chat. On WebAssign, are there set numbers for X and Y, or is it just what numbers work? So it depends on what problem. When WebAssign has like a graph like this where you click on points and it draws the line for you, you can really use basically any number you want. But there are going to be some numbers that are just really hard to actually click on accurately. Like, if you wanted to click on the point, 3 2/3, comma 4.5, like it's just going to be really hard to get that, just right. But a coordinate like, 5, 5 is going to be a lot easier for you to click on. Number one, WebAssign's tool, like kind of tries to, if you're like close to an intersection, it tries to like put your point there. So it's going to be really hard to be a little bit away from an intersection. You can force WebAssign's hand. You can click on a point, and if it doesn't end up just where you want, you can actually go over to the detail of the line. There's a little arrow kind of thing to the right. You can drop down the information about that line. You can manually enter the X and Y coordinates for the point that you want. So you can do that too. If the clicking isn't really working very well, you can get close and then just, if it doesn't end up right where you want it, just change it in the manual detail over there. But usually, sticking with integer coordinates is going to be better. And especially if you like wanted to manually enter something like 1/3 or something like that. I don't know if that little coordinate entry thing accepts fractions. I think it only accepts integers and decimals. So I think in general, if you stick to the kind of guidance I gave up here, getting integer points when feasible, that's probably the best way to go. But there is some sense in which a wider array of numbers or coordinates could be feasible. So yeah, see the WebAssign supplement that I posted on Blackboard for a little more information on how to do that kind of manual entry of those points. That's one of the examples that's in there. Yeah, a good question though. Okay, so if I want to And so I plotted these 3 points and I recognized they were collinear. I know that 2 points determine a line, right? If I put 2 points somewhere, there's a unique straight line, oops, going through them. 2 points determine a line, but in a linear equation, I always plot 3 points as a check, because if I had something like this, I know that somewhere I've made a mistake in one of my coordinates, right? Because I can't have three different lines all representing the same graph. So 2 points determine a line. I plot 3 points, I see that indeed they actually all do fall on the same line. What does this line represent that I've drawn through here? This line actually represents the set of all solutions to y equals 5x plus 1, including, for instance, 3 comma 16 somewhere way up here, but also including, maybe something like uh, maybe like 1 2/3 comma 9 or something, or I guess it would be 1 4/5 comma 9, I think. Um, yeah. Uh, Also, maybe this point here, like -2 comma, my graph is a little bit off, -2 comma -9, something like that. So every point along this line, of course, my line has errors. It's not perfectly straight or doesn't go perfectly through these coordinates. But every point along this line is also a solution, right? If we find a point on this line, we could figure out what coordinates that it's at and add it to this table, and it would be another valid solution, right? So there are tons and tons, infinitely many choices I can make for x. Each of those has an associated y value. I can't list those all in a table, but the way that I might describe that set of all solutions is with a line like this, with a graph. So this is like the set of all solutions to y equals 5x plus 1. Now, it's really only the set of all solutions if we kind of imagine it going off, off up into the right forever and also down into the left forever. So there are going to be some solutions that are associated with like x equals 10 that are way up high, or like x equals -100 that are way to the left and way down. So we need to imagine this line kind of going off forever, in this case, up into the right and down into the left. And then that represents the set of all solutions to our equation. So any xy combination that is on this line is a solution to our equation. And also any xy combination that is not on this line, these would not be solutions to our equation. It kind of makes sense that we have a one-dimensional structure embedded in a two-dimensional structure, a line embedded in a plane, because I start off with two things I can choose kind of freely. I just have x and y. I can choose them however I want. And then I have a constraint that I add on top of that. I say, but you can't just choose x and y any way you want. It has to satisfy this relationship that y has to be 5x plus 1. So if x is 0 and y is 10, that doesn't satisfy that relationship, so it's excluded from consideration. So for each choice of x, if I can select it here, there we go. For each choice of x, there's a unique choice of y that satisfies y equals 5x plus 1. So I now only have kind of one dimension that I can move, and I can choose x any way that I want, but then once I choose x, y is fixed, or vice versa. I could choose y however I want, but once I choose y, x is fixed. Let's look at another example. Here I have the following equation, 3y plus 6x equals 18, and I have three solutions already filled out here, representing the three ordered pairs 0, 6, 2, 2, and 5, uh, there shouldn't be 5, 0. What should that be? 3, 0. I have a typo there. 3, 0. Oh, I actually meant for that to be a typo. So let's actually, I confused myself. Let's go with 5, 0. Okay. This is what happens when I write notes too far ahead of time, then I forget why I did things. So let's suppose that I got this, and you might be asking, well, what about that one? We'll see in a second. So let's graph these. Again, I'll use red so it's easier to see. So 0, 6 is this point here. 2, 2, this point there, and 5, 0, this point here. And I look at this, and I mean, it looks a little bit wonky, right? And it's more wonky than just, the fact that I've drawn a point, and the point that I've drawn isn't an infinitesimally small point. It takes up some space, or it might not be 100% accurate, but it's even a little too wonky for that, right? If I draw a line through these 2 points, it really clearly does not go through that third point. Or if I draw a line through these two, it really clearly does not go through the top left point. This is an indication that something's going wrong somewhere, and I might want to check my work. And indeed, if I go back and check my work, this 5, 0 point is not correct. This should be 3, 0. And if we graph 3, 0, now it makes sense. So I can use the third point as an internal check, right? In theory, I only need 2 points to determine a line, but I always should find and graph 3 points to act as just a way to check my work. And then again, I draw a line through them. I put arrows at the end of the line to indicate that that line extends forever in those two directions. And any point that falls on this line, like say this point or that point, those are also solutions to 3y plus 6x equals 18. And any point that does not fall on the line, like this one or this one down here, those would, or indeed this one here, those would not be solutions to this equation. So this red line represents all solutions to the equation 3y plus 6x equals 18. Or in other words, if I was interested in what's the y value associated with x equals 1, I can come up here and I get 4, right? 6 times 1 plus 3 times 4 does look like 18. So I can use the line to help me find more solutions, or as a guide for whether or not a certain coordinate it does represent a solution to the equation. Okay, so let's work through these two exercises. Let's take about maybe 6 minutes for this. I think at this point, the equation solving and so on should be going fairly quickly. So let's take about 6 minutes for this. I will go through and fill in the table here as we're going along. And then when we come back together, I'll do the graph for both of these with you guys. So, imagine that you had one of these kind of negative 10 to 10 graph setups here under each of these problems. I can't actually put it there because if I put it under the first exercise, then it'll push the second exercise way down. But imagine you had one of those there. Or actually I can put it there and then make it smaller. And then we'll just enlarge it when we do the answer. So we have this here, plot your answer on this graph. Obviously make it a little bigger so you can see it. I'm making it smaller so we can keep the other exercise on the page. But work through these two exercises, uh, fill in the tables, plot the 3 points, draw the line, make sure that your line goes through all 3 points, and repeat that for the second one. So we'll come back together in probably about 6 minutes or so. Okay, let's take a look at these two exercises. So for the first one here, when x is 1, y is 2, that's a pretty nice point to plot, 1 comma 2. When y is 14, x is 5. I mean, that's an integer coordinate, but I don't really want to plot 5 comma 14. That's going to be off of my standard negative 10 to 10 square window. And same with when y is 0, x is 1/3. That's in the window, but 1/3 comma 0, that's not an integer point. I would prefer an easier point to plot. So let's try to figure out two other points that are easier to plot. And again, I see if I kind of pick integer values for x, I'm going to get integer values for y. And if they're moderate values for x, I should also get moderate values for y. So if I try x equals 2 and x equals 3, I get y equals 5 and 8 respectively. That gives me two more points that are nicer points to plot than the other ones that I've kind of xed out up here. So I'd rather use the first point along with these two extra points to plot my graph rather than the original three that were given. Now, I'm going to try to get OneNote to cooperate with me here, so fingers crossed. Okay, select all of this, cut, and I'm going to paste a little further down here. Would that work? Well, it's in like its own window, but all right, well, that's close enough. Put it in its like own separate window. And, oh, window now, and it got the windows confused, but close enough for what we need, I guess. All right. Now let me expand this. Come on, OneNote. Trying to get it to let me. There we go. Almost had it. I love OneNote when it works. There we go. I need a placeholder so that I can expand this window a little bit. All right. So that I can move this down a little bit so that it's not. There we go. All right. Sorry, that was a lot more complicated than it really needed to be. But welcome to Microsoft. I feel like everything in Microsoft is a little more complicated than it needs to be. But I will say the OneNote's copying functionality has gotten a lot better since I started using it a few years ago. But okay, so what are our 3 points that we're going to plot? The first, and then these last two. We have 1 comma 2. We have 2 comma 5, and 3 comma 8. And yeah, these 3 points do seem like they're collinear. They do lie on the same line, so they kind of act as an internal check that it seems like I've done my algebra correctly. Draw a line through them. And this is my graph of y equals 3x minus 1 using these 3 points. Now, again, could you have used, x equals 0, y equals -1? Sure. We see that I missed that point a little bit here with my line because it's not quite straight, but we're going more for a schematic here than being completely accurate. If I was doing this with pen and paper, I might actually break out a ruler or even just like the side of another pencil or something to draw the line a bit straighter. But I think OneNote can do that, but it's kind of a hassle to get it to draw a straight line the way that you want. So drawing it freehand here, it's not a super straight line, but we're getting a schematic diagram of the graph. And then, all right, cross your fingers again. I think this one should go a little easier. We've got our windows all wonky, these little sub windows in OneNote, but I think we can work with that. I don't think it'll cause a problem. All right. For some reason, my alignment got a little messed up here too, but I think we can tell what's going on. So the 3 points we want to plot are 0, 2, 3, 3, and negative 6, 0. So 0, 2 is here. 3, 3 is here. And negative 6, 0 is here. The negative 6, 0 is kind of a little farther off to the left, but it does kind of look like they're in a straight line. And again, especially with me using like a trackpad in my hand, kind of stuttering along it. Not the prettiest graph in the world, but I think we get the idea. So using these 3 points as a guide, I draw my line through those 3 points, my straight line, and every point on this red line represents a solution to this equation. And any point that's not on the red line is not a solution to the equation 6y minus 2x equals 12. Any questions on this? Okay, so let's take a look at another example. We'll go through this one a little more quickly. So here we have y equals negative 2x plus 8. So when x is 0, y is going to be 8. When x is, let's say, 1, y is going to be negative 2 plus 8, or 6. And when x is 2, y is going to be negative 4 plus 8, or 4. So I have 3 points, 0, 8, 1, 6, and 2, 4. Those do look like they're on a straight line. I can draw my line through them. And that's the graph of y equals negative 2x plus 8. So we actually see that this graph kind of goes from top left to bottom right, where my previous graphs have all, or will have mostly gone from bottom left to top right. I guess not this one here, but the previous two that we just did. So one thing that we don't really talk about in Math 90 is the idea of slope. That's more of a 108 topic, but just to really briefly touch on that, if I have a graph that's pointing kind of upward like this, bottom left to top right, when I increase the value of x, the value of y increases. But when I have a relationship like this, when I increase the value of x, the value of y decreases. The two kind of work in opposite ways. Let's skip over this one. And let's come down to these two exercises. And so these have a little more freedom. Find 3 solutions for the equation, plot the 3 solutions on a plane, and then graph the equation. So let's take about 4 minutes for this. We'll be a little more aggressive with our time because we've had practice coming up with solutions, quite a bit now. We've had practice plotting points quite a bit now. I think we should be a little better able to combine the two together. So let's take about 4 minutes for these two, and then we'll come back and discuss them. Okay, it's just about 4 minutes, so hopefully you at least got most of the way through these two. Um, so we see, these should be familiar equations. We've seen both of these equations before. Um, and we see when x is 0, y is -7. So 0, -7 is a point, 1, -2, and 2, comma 3 are three good points to use. You could probably find another one or two that would be good candidates as well, but I chose these three. I plotted these, and I noted they did all fall on the line, so that's kind of an internal check to my work. So I draw a line through the three of them, and even if you used different points to plot, you might have used one that's up here somewhere. What would it be like? Maybe 3, comma 8. Does look like we go through there, so my line is more accurate than usual. But if you had used, say, this 3, comma 8 point instead, you might have different kind of reference points to anchor your line, but you should have the same line that I have here. It should look very similar to the one that I drew here. Okay. And then similarly for the second exercise, the 3 points that I chose y equals 0, 1, and 2, giving x equals 8, 5, and 2 respectively. But there will be lots of different choices that you can make here, particularly for y. You can make a couple other choices for y and get points that are going to be within this -10 to 10 on both of the coordinates and our integer points. But we see we have 8, comma 0. We have 5, comma 1. And we have 2, comma 2. And again, those look like they're in a straight line. I don't have a point that's, up here or something like that, where I think that I might have made an algebra mistake. These look like they're on a straight line. So that's the graph of my line. That's the graph representing the solutions to 3y plus x equals 8. And again, you might have used uh, different points. You might have used different anchor points, like say maybe what y equals well, y equals -1. Uh, yeah, not y equals -1. If we have, say, yeah, x equals -1, y equals 3. It looks like I kind of missed that one. Probably should go a little more like this. That was just my straight line not being all that straight. But so you might have used that one. I had to think twice about that math because it looked like I was missing that point, and it was just my line isn't quite straight. If you had used this point as your anchor point instead of, say, one of these other three, your points that you use to draw the graph might be a little different than mine, but your graph of the line, this line should look the same as mine. I mean, plus or minus my ability to draw a straight line, apparently. So, uh, any questions on these? Okay, let's take a look at a problem like this. Graph the following linear equation: y plus 5 equals 2/3 x. Maybe take about 2 minutes and work through this one. So start working through it on your own. I'll pretty much work right alongside you, and then in about 2 minutes we can come back and discuss the answer. So take about 2 minutes for this one. Okay, it's just about 2 minutes. Um, and again, you might have used three different points that I used, but your line should end up looking the same. You might have used, say, 9, comma 1. But what I did is I saw, okay, I have a 2/3 x over here. If I just pick the values of x to be multiples of 3, that'll get rid of that fraction. I don't have any other fractions in the problem. That should give me nice integer coordinates. So x equals 0 gives me y plus 5 equals 0. Y is -5. So 0, -5, my bottom left point here. If x is 3, 2/3 times 3 is 2. So y plus 5 equals 2, or y equals -3. So 3 comma -3, my kind of middle point on the graph. And then if I pick x equals 6, 6 over 3 is 2 times 2 is 4. I have y plus 5 equals 4, y equals -1. So 6 comma -1, my third point. You might have used a point like, say, x equals 9. 9 over 3 is 3 times 2 is 6. Y plus 5 equals 6. Y has to be 1. So you might have used, say, 9 comma 1, or you might have used a negative value for x, maybe x equals -3. You might have gotten different anchor points, but your line should look the same as mine. Any questions on that? Okay, let's look at a few special cases. So far, I've kind of made a couple of statements that are almost always correct, that have always been correct in the examples we looked at, but that sometimes aren't so correct. So one of the statements I made so far, or up to this point, is something like, um, each time for each value of x that I choose, I can find a unique associated value for y, and vice versa. For each y that I choose, I can find a unique x. So if I'm interested, for whatever reason, in x equals 4, I can use the graph to estimate the associated value of y when x equals 4. Or if I was interested in y equals -6.5, I could again use my graph to estimate the value of x when y equals -6.5. So I can choose x essentially any way that I want, and that x is going to be associated with a solution, with a point on the graph, with a solution to the equation, provided I choose y the right way, and vice versa. We have some special cases. We have some edge cases, though. Let's take a look at those. So let's consider the equation by equals c. Here we're thinking of b and c as being numbers, being constants, and y as being a variable. So we might think like, an example like 3y equals 2. Importantly, the context that we're in actually affects the meaning of this statement. This is a linear equation, but it can be a linear equation in one or two variables. We could either think of the solution as looking like a single number, the number y equals 2/3, or being a set of points on the line. What do we mean by this? Let's look at an example. Let's take the one variable case. So here my context is there's only one variable under consideration. I have no idea about any other variables. Y is the only variable here. So I have 3y equals 2. This is kind of like I guess a chapter, what was it, chapter 2 problem. Y equals 2/3 is the solution. If I substitute in 2/3 for y, both of my sides of the equation match, they balance, I get a valid solution. If I want to represent that graphically, I might go over to my number line and at about 2/3 or so, plot a point there. If my context is that I'm dealing with one variable, y equals 2/3 is the number that represents the solution to this linear equation. What if my context is that I'm in two variables? by plus c now takes on kind of a different meaning. If I think of it being like standard form, ax plus by equals c, really this is just like ax plus by equals c when a is 0. A could kind of be any number, right? So a could be 0. And actually, I noticed that since 0 multiplies x, if I were to choose x equals 10 and say, what's the associated value for y? Well, the 10 gets multiplied by 0, it just kind of disappears. Or if I pick x equals -5, that 0 just kind of blasts the x, right? So whatever value I choose for x really doesn't have any impact on whether the point under consideration is or is not part of the part of the solution set. So in fact, I can kind of choose x any way that I want. I can choose x to be 5 or -10 or plus 100 or whatever, or pi over 2, whatever I want. It's not going to have any impact on whether the point under consideration is a solution. The entire impact is going to be on what my y coordinate, or is going to come from what my y coordinate is. So again, if I have like 0x plus 3y equals 2, I still have this kind of idea of y equals 2/3, but now in the context of two variables, really kind of what I'm saying is y always has to be 2/3 for this to be a solution, and x can be anything. So any point that looks like something comma c over b or something comma 2/3, any point that looks like this is a solution. 0 comma 2/3, 1 comma 2/3, -10 comma 2/3, pi comma 2/3. I can put whatever number I want in for x as long as the y coordinate is 2/3. It's a valid solution. So remember, this is my x axis and my y axis. So here I am at y equals 2/3 when, say, x is 0, so at the point 0 2/3, or at 1 comma 2/3, or at 10 comma 2/3, or -10 comma 2/3. I see that this set of solutions, this set of points, makes a straight line, but it's a horizontal line. So our first special case is where we have two variables and x doesn't appear directly in the equation. Right? So there's no explicit dependence on x. Again, we are in the context of two variables, so the variable x kind of does exist, it just doesn't come into play in this constraint, in this equation. So x is kind of a free variable, as it's sometimes called. It can be anything you want, but y has a constraint. Y's constraint is not related to the value of x. It's kind of disjoint from x. Y always has to be 2/3 in order for us to be a solution. And it doesn't care what x is. X can be whatever, as long as y is 2/3, we have a solution. So we only have a constraint on the second coordinate. On the vertical coordinate of our point, the horizontal coordinate, the x coordinate, can be anything it wants. This is a horizontal line. So it's a line that's horizontal, it's parallel to the x-axis. Because I can choose x any way that I want, I just have to always have the output y equals 2/3 for my y value. Or more generally, y equals c over b. The other special case, you could probably guess what it is. Well, it's when we have, say, ax equals c, when y doesn't explicitly show up. Again, constants a and c, variable x, and again, the context affects the meaning. If our context is that we are talking about a one variable situation where x is the only variable floating around. We don't know anything about a variable y. So if I have, let's say 7x equals 5, then x equals 5/7 is the number that's the solution. So it's maybe something like there. And I can plot it on a number line, and that's my solution. But in the context of two variables, if I say, okay, I have two variables, x and y, they're related in some loose sense by this constraint equation, ax plus 0y equals c. Well, again, whatever value I choose for y, it immediately gets multiplied by 0 and disappears. So ax equals c really is only a constraint on the x coordinate. So again, if I have, what was it, 7x equals 5, well, this tells me my x coordinate has to be 5/7, but my y can be anything. So 5/7 comma whatever is going to be a solution to this equation, 7x equals 5. So that could be 5/7 comma 0, or 5/7 comma -1, or 5/7 comma 3 pi, or anything else that you'd like to put in there for y, any other real number. So as long as the x coordinate is 5/7, if we're at 5/7 comma 0, or 5/7 comma -1, or 5/7 comma +1, anywhere along this vertical line, this vertical line where x is 5/7 and y can be whatever you want, those are all going to be solutions to 7x equals 5 in this context of two variables. Y is kind of a free variable. It can be whatever it wants because it doesn't explicitly show up in the constraint equation. It's only x that explicitly shows up. Any questions on any of this? Okay. Now, the last section that we're going to cover in chapter 4, graphs with intercepts. If you understand graphing with intercepts really isn't a very difficult concept. The main ideas that we are introducing in section 4.3 is what is an x-intercept and what is a y-intercept. And we've actually kind of been using those all along. So what is an x-intercept and what's a y-intercept? I'm going to give myself a little room here. So if I consider an equation like ax plus by equals c, and let's suppose it's not one of these special cases. So maybe the graph looks something like this. I have my x and y axes, and I have the graph of the equation ax plus by equals c, this line that represents all of the points whose coordinates represent solutions to ax plus by equals c. I know that there are lots of points in this line, like this one, or this one, or this one, that represent solutions, but there are a couple of nice points that are quite useful for me. Specifically, where this line, ax plus by equals c, intersects CTS, the axes, the y-axis or the x-axis. Those points of intersection are called intercepts. So kind of a two close words there, but we call this one the x-intercept and this one the y-intercept. So most lines, the lines that aren't special case lines like those previous two cases, are going to have an x-intercept and a y-intercept. the intercepts are the points of intersection. So this is the x-intercept is an ordered pair. It's an ordered pair when x equals a, and notice that the x-axis is located when y equals 0. So the x-intercept is going to be a point a comma 0 for some x value a. So when x equals a, y equals 0. And the y-intercept is going to be the point, the ordered pair. We'll call it 0 comma b. When x is 0, the point of interest is on the y-axis. And if I figure out what y has to be in that case, that point 0 comma b is the y-intercept. So really what we're saying is if I choose to plug in x equals 0, figure out what y is, that point, that ordered pair, is the y-intercept. And if I choose to plug in y equals 0, figure out what x is, that's the x-intercept. And when we were coming up with 3 points on our own to try to graph a linear equation, we quite often started with, let's see what happens when x is 0, let's see what happens when y is 0, because 0 is a pretty easy number to plug in. It just, whatever's multiplying it, the whole term just goes away. So we, have actually used intercepts quite a bit in our previous graphs, right? This 0 comma -5 was a y-intercept. This one here, what was it? 8 comma 0 was an x-intercept. We didn't really call them that at the time, but we've been using them all along because they tend to be easy points to find. So let's find the x and the y-intercepts from the equation 3x minus 5y equals -15. Let me zoom this back in. I zoomed out a little bit for those graphs. Okay, so remember when x is 0, that gives me the y-intercept. X equals 0 tells me that -5y equals -15 says that y equals 3. So 0 comma 3, this is a point on the y-axis, is the y-intercept. And analogously, if I choose y equals 0, then I get 3x minus 0 equals -15. That says that x equals -5. -5 comma 0 is a point. It's when x is -5 and y is 0. That's on the x-axis. And that is the x-intercept. If I can find the two intercepts, I only need 2 points to plot a line, right? There's 0 comma 3. There's -5 comma 0. I can plot the line using the intercepts. The intercepts are often fairly easy to find. Not all the time, but often they are. Sometimes they end up being, fractions or something that are a bit of a pain, but but they're often easy to find in nice coordinates. Um, and we can see that gives us 2 points. We can determine a line from 2 points. Now, we probably would also want to find a third point so that we could kind of check and make sure that that third point does fall on this line. And so so that we have a way to check our work. So we probably still would want to find a third point just to check, but strictly speaking, it's not necessary. We could get the graph from just the intercepts. Okay, so 2 exercises. Let's take about 2 minutes for this. This should go pretty quickly. Find the x and y intercepts for each of these 2 lines. And note this second exercise. Give a little bit of thought there. It's not going to be quite as algorithmic as the previous one. So give a little thought to the second exercise. Maybe ask yourself, what's the graph of the line going to look like? And what should the intercept or intercepts be? All right, so take a couple minutes for this exercise. Maybe we'll take about 3 minutes so you can have a little more time to think about that second one, but 2 to 3 minutes for these two. Okay, let's look at the first exercise here. Finding the x and y intercepts here. We have kind of a nasty looking fraction equation. I don't think it's worth it to clear fractions here because we're looking for intercepts. We're going to be plugging in x equals 0, y equals 0, and that's going to simplify things quite a bit. When x is 0, we have 3 halves y equals 3/4, or y equals 1/2. So the point 0, comma 1/2, x equals 0, y equals 1/2 is the y-intercept. It's the y-intercept because when x is 0, the y value tells us the height, so that's our y-intercept, right? We're on the y-axis. Or when y equals 0, we can plug that in, we get negative 1/3 x equals 3/4, or x equals negative 9/4. So negative 9/4, comma 0 is the x-intercept. Now, our intercepts are what they are, right? I can't say, oh, I don't like that y-intercept because it's has a fraction in it. Uh, find me a y-intercept that is at an integer point. No, the y-intercept is the y-intercept. So I might be in a case like this on, say, a WebAssign plotting problem where maybe I don't want to plot 0, comma 1/2. So I'll choose a different point, right? So the intercepts aren't always great points to plot. You know, they might end up being fractions, or you might get, 0, comma 25 or something as the the y-intercept. But nevertheless, these are the intercepts. For the second exercise, we kind of have an interesting case here, right? Y equals 5x, we plug in x equals 0. We're looking to find the y-intercept. What is the height on the y-axis where the line intersects? But we actually get y equals 0. Y equals 5 times 0 is 0. 0, 0 is the y-intercept. Actually, the origin turns out to be the y-intercept. But of course, the origin is also on the x-axis. The origin must also be then the x-intercept, right? If I plug in y equals 0, I get x equals 0 as the association. 0, 0 is also the x-intercept. So in this case, where our line goes straight through the origin, I actually can't use the intercepts, or just intercept in this case, by itself to plot the line, because I only have one point. I know the line goes through 0, 0, but I would need another point, like maybe 1, 5, or -1, -5. I'd need to supply a second or maybe a third point to plot the line or to check my work. So if the one intercept is at the origin, the other intercept is automatically at the origin as well. And then I need to come up with another point to use to plot my line, and probably a third point to check my work would be a good idea. And then one just last little note is, note that the special cases do kind of have intercepts, but really each one only has one intercept. The horizontal line has a y-intercept, but no x-intercept. It's parallel to the x-axis. I suppose if we had a horizontal line that was y equals 0, then kind of every point is on the x-axis, and then it's, I don't know whether I call that an intercept. I don't know whether I'd say it has infinitely many intercepts or no intercepts. It kind of seems like a very strange case. But we see the vertical line has an x-intercept. It crosses the x-axis, but no y-intercept, right? My points all look like, for instance, 5/7 comma something. So 5/7 comma 0 is valid, but 0 comma something, well, that can't be a solution because the solutions have to have 5/7 in the first coordinate. So my special cases, they only have one intercept, and also the kind of edge case where my line is not one of those two horizontal or vertical special cases, but where my line passes through the origin, through 0, 0, that also only has one intercept, the point 0, 0. And really, I guess in any of those three cases, if I just have my intercept, I only have one point, not enough to draw a line. I need to supply a second point. I need to just come up with a second point like we've done, many times in the past, like here, for instance, just come up with a second point. That gives me enough to draw my line. And then I probably also want to come up with a third point so that I can check that it's on the line and check my work. So that actually wraps up our discussion. I told you 4.3 was pretty short. That actually wraps up our discussion of chapter 4. Again, there's more material in chapter 4 in the book, but we're not going to be covering that. And that, of course, will not be material on the exam. So again, exam next week. I'll make an announcement next Tuesday and Thursday as well. Plan to take it no later than Thursday night. And the sample exam I'll have posted pretty shortly, probably before 11 this morning. All right. Let me stop the recording here.